bit over the last few years. So the work I'm going to talk about is work that I've been doing over the last 5 years or so with a great range of collaborators, and it concerns out of equilibrium properties of quantum critical systems. This slide is a bit of a rallying cry. As usual with these rallying cries, they're best used amongst the community who's working on the same sort of problem. So if I were talking to a non-equilibrium crowd, I'd be saying, oh, well, this is the great scientific frontier, understanding the out of equilibrium behavior of systems. And to an extent, I think that's true. But one of the key things about out of equilibrium systems is that there are fewer overriding principles that we know of. You know, the rules of statistical mechanics really constrain equilibrium behavior, but the out of equilibrium isn't so constrained. Really, this work over the past few years has been driven by this idea that quantum critical systems have universal spatial and temporal scaling. And since out of equilibrium steady states in particular are typically determined by dynamical properties, we might hope that the dynamical scaling that you find in equilibrium is inherited by an out of equilibrium steady state. And there have been a few results, actually an increasing number of results that have shown this. The first one I know of, actually due to Philip and his collaborator. And then Shivaji and I'll talk a bit about this work, and an increasing number here actually. This is probably far too short a list. And in particular, that holography has got something to say. I mean, we can typically, in the field theory, derive results deep in the non-equilibrium regime, but holography, it seems, can allow us to interpolate between the equilibrium and out of equilibrium results. So when we think about out of equilibrium quantum systems, we normally have this operational division of systems into steady state out of equilibrium and sweeps and quenches. And I'm going to talk about out of equilibrium steady states, and here's a few papers here. One particular paper I'd like to point out, that's quite a recent work by Benjamin Doyen and Bernard, concerns a system that really can be put into either of these, either steady state or a quench. And this is a system where you take a 1D system, integral system. You start with two separate semi-infinite lines prepared at temperatures T1 and T2. And if you let that evolve in time, you find that you get some universal out of equilibrium region in the center. And the size of this increases in time. So, we might think of this as a quench. We're starting off the system with in some state and letting it evolve, but actually it has this out of equilibrium steady state in the middle. And actually, the reason I point this out, you might wonder when you hear the talk, because it apparently has very little to do with this, but the point here is that the way in which we couple to the bath is very subtle in these systems. And it can have an important effect on the types of system that we see and some type of results that we see, whether we see universal behavior or not. And we have to think quite carefully about how we engineer our out of equilibrium systems. So here's a brief outline. I'm going to focus on this Bose-Hubbard model in 2 dimensions. It's an example that we have under quite good analytical control, and we can hope to learn new things from studying that. And I'll say a little bit about equilibrium transport, and then I'll go on to out of equilibrium transport, and I'm going to give 3 different ways of calculating this out of equilibrium behavior. And each one of these will show something new, something different about the nature of this out of equilibrium universal steady state. And then we'll discuss over wine, I guess, afterwards. Okay. So this section, nothing in this equilibrium section is my work, and a lot of it is actually due to Sabir. So, as you know, the Bose-Hubbard model, it's a model for bosons hopping around a lattice with some tunneling between sites of the lattice and some repulsive interaction on site. And it has a continuum field theory that looks a bit like a Klein-Gordon theory with a phi to the 4 interaction. And where if we have very strong hopping, we have essentially a superfluid. If we have very strong repulsion, we have an insulator, and we're interested in this quantum critical point between the two that dominates the system's behavior over a broad range of system parameters and temperature. And we're interested in this quantum critical regime where, in fact, thermal and quantum effects are extremely difficult to disentangle, and on the face of it, that makes the problem very difficult to solve. But actually, in a way, it's this that simplifies matter. It leads us to this emergent scaling behavior, and we have this universal spatial and temporal scaling in these systems. So I'm interested in the two-dimensional Bose-Hubbard model. I'm going to apply a strong electric field, and you can use this sort of scaling analysis in equilibrium to deduce what the form of the conductivity might be as you deviate from the quantum critical point.
Do you really need to have mu in the denominator, or should it be z?
It should be z. Okay, so a lot of my discussion is going to be around these Boltzmann equation analyses of these systems. So Kedar-Domley and Super taught us this lesson that this limit of omega over t going to 0, which is the limit we're interested in for our DC conductivity, doesn't commute with any other approximations. And so they developed this real-time Boltzmann technique, initially in the epsilon expansion, in order to deal with this. Actually, there's this nice recent work where they show another way of analytically continuing results using results from holography. Okay, so this paper in '97 it basically wrote down a distribution function, an equation determining the distribution function of the normal modes. So you take the Klein-Gordon equation, it has positively and negatively charged modes, and under this 5-to-the-4 interaction, they're going to scatter off one another. We develop an equation of motion for the Wigner distribution of those modes, and it looks like this. And all the criticality is in the form of this scattering integral here. And the usual way, as kinetics matter physicists, we approach such equations is just to expand about a thermal distribution, and then we can, if we can invert this linearized scattering integral, we have a solution to the problem. And if you do this, you find that you get this nice result for the conductivity. The point is that this technology basically ends up describing the following situation. So we have some thermal equilibrium distribution that in this case, because we're dealing with bosons, would just be a Bose distribution with some width of order temperature. And we apply our electric field, and that shifts the distribution in the direction of the electric field. And the shift is proportional to the electric field, actually divided by temperature here. And you can see that this sort of linear response analysis will work, provided that this shift is smaller than the width of the distribution. That's when linear response works, but you can see it's going to fail when the electric field is big enough. At any given temperature, there'll be a field scale where our linear response isn't going to work. Now, I told you that the central idea here was that the dynamical scaling might be inherited out of equilibrium. And we could just guess here that maybe we can take this equilibrium phase diagram with the Z. Thank you, Philip. We could instead draw a similar phase diagram where we have some energy scale that's determined by some power of the electric field, and maybe we can translate all of these results across. So, in fact, that is largely what we end up being able to do. But we have to turn this type of scaling analysis into a calculation, and that's what I'm going to try and demonstrate in the next few sections of this work. So I'm going to start off with a 1 over n expansion version of this. And actually, when we're trying to solve some Boltzmann equation like this out of equilibrium, we have a few problems. In particular, well, here we have a very strong electric field, and it turns out that will produce pairs of these normal modes from the vacuum by Landau-Zener tunneling or the Singer mechanism. But our central problem is that we can't actually linearize this equation when we're out of equilibrium. And moreover, we have Joule heating, which we heard about in a very nice talk this morning. So when we were dealing with this problem, we struggled actually to find a way to analyze this. And we came up with a trick, really, within a 1 over n expansion, where we took a large number of copies of this theory. We chose to only couple one of them to the external field. That means that the other n minus 1 copies, if you like, provide a zero temperature bath, and moreover, the scattering integral reduces to something very simple, where we can get an expression for this constant here in terms of our scattering integrals in a large n limit. And you can see that this just leads to a decay, essentially a decay of our energy into this zero temperature critical bath. And we can just integrate this equation and get a solution. So that was our 1 over n expansion. And it has a solution that's very, very asymmetrical in field. So this is, say, the distribution function of the positively charged modes. And you see it has this extent in the direction of the electric field that is much longer than the width of the distribution. And this width is more or less determined by the Landau-Zener tunneling rate. Okay.
That's a steady state.
It's a steady state. Okay. So let me give a little scaling analysis version of this. So we can take this equation, and if we multiply it, probably we have to multiply it by the velocity and sigma, the charge of our carriers, and then integrate and sum over the charges. We can get an equation of motion for the current. And this term here is the combination of the the Singer per production and the driving term, and then we have a term here that's the decay. And you can see we could just solve that for in a steady state. We get something that just tells us that the conductivity is constant in 2 dimensions. And this is the result that we heard about this morning when the conductivity when we're in 2 dimensions. In fact, in 2D, the conductivity is independent of temperature. That power law was d minus 2, and so you might have guessed, well, our energy scale it depends on the electric field. We change the field, the effective temperature isn't going to change, so maybe the conductivity stays the same. And in that sense, this result wasn't very revealing, but it turns out that the current noise is a bit more revealing. This was the next bit of work that we did on this with Joe Moore and Shivaji again and Ashwin Vishwanath. We use this Boltzmann-Langevin approach. Basically, the scattering is a Poisson process, and so we can model this by adding some noise term to this equation that basically has a rate that's a noise term whose correlator has the square root of the rate of the scattering process as a prefactor. And if we integrate this, we find that we get a noise power that goes like the square root of the electric field, which is quite unusual. Well, normally you'd expect the noise at very low temperatures to go linearly with the current, to be a sort of shot noise result. And this you could interpret as some very strange 1 over square root electric field dependence of the effective charge. But actually a nicer way to interpret it is to say that this is more or less Johnson noise at an effective temperature that goes like the square root of the electric field. Remember, though, that the distribution function was very far from equilibrium, but the current noise has this apparently thermal equilibrium form. So where does the holography come into this? Well, basically, I'm going to tell you how we can model this with this D3, D5 intersection. But at very low temperatures, we have this Johnson-Nyquist noise. We know it should go like the product of the conductivity and the temperature. And at this very high field limit, we have something that looks like the product of the conductivity with the square root of electric field. And it turns out that the holographic result is going to allow us to interpolate between these two. So to take us right from the thermal equilibrium result to the high field result. And this is going to happen because effectively the Hawking radiation coming from our D3 horizon is going to cause current fluctuations in the boundary, and they will mimic the current moves. Okay, so aspects of this, the steady state current were worked out by Koch and Sondy, and then I did this work with Julian Sonner, came out earlier this year. Should say, following Philip's caveats about his talk, I'm not a string theorist. So the details of this, many of the details are done by Julian, but I'm going to try and run through them quickly here. So this D3, D5 intersection is some theory where we have many 3 branes, and they're intersecting with this 5 brane. And the point about having many D3 branes is that they basically determine the metric. And we're not going to have any back reaction of our gauge fields on that metric. And we're going to be interested in the dynamics, in solving our equations for gauge fields on this D5 brane. Okay, and actually this fact that we have many D3 branes, many more than we have D5 branes, is very similar to the trick that we used in the field theory, this 1 over n trick. Basically, it allows us, well, it's in the probe brane limit, it allows you to treat something in steady state, and all the subtlety of how the energy gets from your steady state distribution into your bath is sort of swept under the carpet. And if I have time, I'll spend 2 minutes at the end saying how I think one might get around this, or how one might address this problem head on in an epsilon expansion calculation.
With the end, this is all doable to some CFT3 or not?
I guess that's the idea. Yeah, that's the idea.
So the number of infinite directions are the same for both the D3 and the D5. I myself, I'm not a string theorist.
Well, so this little drawing here tells us where the branes are localized and where they're where they're open and where they're localized.
So the U direction is infinite or not? Oh no, the U direction is the holographic direction.
Yes. Yes. So the D3 isn't extending that direction. It's just this stack of branes here, and the D5 does extend in that direction. It has this radial direction. So we're looking at the gauge fluctuations on this D5.
Well, so from here it looks like as if some particles in a CFT3 are scattering off of the particles in a CFT4. Is that correct? It's like it's like a critical system with the boundary of a 4-dimensional.
It's like a defect.
Yeah.
Like you have a defect.
Right.
4-dimension 1 defect.
So Gordon Semmelhoff explains it as you're basically something like V, right? With fundamental particles on there, fundamental quarks interacting with one higher dimensional monoclinic citation.
Yeah. Right. Okay.
That's what I would have said. Had I been a string theorist.
It's actually quite scary.
Okay, so the steady state solution of this was actually this Koch-Sondy paper, and it's quite neat. You can use this Koch-O'Bannon trick as Julian taught it to me. Basically, we write down the equations of motion for our gauge field in the radial direction. Now we end up with this square root form here, but it has to be real. So we can just insist that these 2 lines here are 0 at the same point. And this gives us automatically a solution that the current is proportional to the electric field. But also we get out of this that the point where the denominator and the numerator vanish is actually a point where there's a new horizon induced on the D5 brane. So life in the D5 is different from this life in this 10-dimensional space. The horizon is in a different place, and it's in a place that's modified by the electric field. So we were interested in looking at gauge fluctuations about this, and to see if they could mimic the current fluctuations that we found at the boundary in our 1 over n calculations previously. And in fact, it turns out they do. So the calculation, so this equation is basically the simple harmonic oscillator equation. So the gauge fields in the bulk, you can linearize the action for those and linearize the equation of motion for those, and you get this, which is just an equation for a harmonic oscillator in tortoise coordinates. And so at the horizon, we have Hawking radiation that's emitted with a thermal distribution at this modified temperature, and they propagate all the way to the boundary where they remain thermal at this modified temperature. And you can, using some sort of Keller's field theory, you can write down a Boltzmann-Langevin equation for the gauge field on the boundary, and that's conjugate to the Boltzmann-Langevin equation that I wrote down a few minutes ago for the currents. And so you recover the same results. Actually, when we started, we were fiddling around with this trailing string work of Son and Tini to try and get at this. And actually, it's rather simpler in this case. We could just solve the equation throughout the entire bulk. And normally when that happens, you think, well, we're doing the right thing because it's so easy to solve. So it's quite a pleasant experience for my first attempt at being involved in one of these calculations. Okay, so here's the result. We get this current noise, which is at this effective temperature. And crucially, the fluctuations on the boundary are thermal, even though our distribution is clearly not thermal. So the point is that this temperature is different from the background temperature in this 10-dimensional space. And the fact that we have these different temperatures tells us that our system is not in thermal equilibrium. It's an out of equilibrium system. Yet, this current noise has this apparently thermal distribution. And we might ask whether this is general principle. In fact, there are other cases in condensed matter where people have worked with field theory approaches, in particular tunneling into a quantum dot where you have leads at two different potentials. Chimiao C and Stefan Kirchner have found in that case that their distribution function is far from thermal, but the fluctuations have a thermal distribution at some effective temperature. So I don't know the answer to this question, whether it is a general principle or not, but it seems quite suggestive here. I think in general, possibly certainly the way the radiation is emitted from this stationary horizon has to have a barothermal distribution, and the way it impinges here then presumably is also thermal. I wonder actually in the case of this growing black hole that we were told about this morning, whether one has a similar situation. Okay, so I'm aware that I stand between you and your wine, and I have one more section that I was going to talk about. So I'm going to try and keep this brief, but the whole point of this section is to say that one has to be very careful actually about coupling to the heat bath in order to achieve these universal out of equilibrium behaviors. And in fact, it was realizing this that led Shivaji and I to avoid trying to do this calculation within an epsilon expansion initially. So if we try to study the system within an epsilon expansion, we can't use this 1 over n or pro-brain trick. We have to face head-on the question of how do we get this dual heat out of our system if we're going to describe a steady state. And essentially the question of whether we get universal behavior or not is determined by which is the rate-limiting step in getting the heat out of our system. And if that rate-limiting step is universal, then we have a chance. If it's not, then we don't. I mean, it will not be universal. So in particular, the transport of heat to the boundary of the system is going to depend on the size and shape of the system, and that will be non-universal. And actually, that's usually the case when you take a piece of conductor and you put a voltage across it. It heats up, and it heats up to a temperature where it's in some steady state with the radiation out of the resistor, and that depends on its size and shape. Now, if the transport to the boundary of the sample is very rapid, then you can have a chance that the scattering into those transport modes might be the thing that determines the steady state. And if that's the case, you have a chance of finding a universal steady state. And for the Bose-Hubbard model, the thermal conductivity is infinite. And it's that allows us to see this universal result. So we need to turn that into a calculation. The Boltzmann equation looks just like the one that I wrote down before, but previously I didn't have to worry about spatial dependence of this solution. Now I have to do a calculation that's formally on a finite sample, and gradients of the distribution function drive heat flow in the sample. Oh, I've missed a bit there. So the point is that when the thermal conductivity goes to infinity, then the gradients that you require to drive a sufficient heat flow that will compensate the Joule heating, so the gradients that you require to compensate the Joule heating goes to zero. And so we might hope to analyze this within some gradient expansion. And actually what you can do is, if you do such an expansion, you can eliminate the gradients of the distribution function in favor of a sink term that describes how energy is scattered from your current carrying modes into your heat current carrying modes. And then they very efficiently take that heat to the boundary of your sample. And this can be a universal function. It's determined by the zero modes of the scattering integral, linearized about whatever your non-equilibrium steady-state distribution is. So, well, you can do this, and this is my postdoc Andrew Berridge has shown how to do this, but you still have to deal with this scattering integral, which is very nonlinear, and we're far from thermal equilibrium. So what do we do? Well, quite often in condensed matter, one's first guess will be that we'll linearize about some thermal distribution with a self-consistently determined effective temperature. And Andrew tried this, but it doesn't converge. That's sort of an indication that this distribution, this steady-state distribution, is far from thermal equilibrium. And instead, you can take some ansatz distribution where you've done opposite Lorentz-Bus of the positive and negatively charged carriers. Well, why would you think that would work? Actually, if you just do a Lorentz-Bus of positively and negatively charged carriers, then the scattering integral is zero on that. And so most of the terms are zero on this, but we have some residual ones we might hope that things are controlled.
You don't have to put any spatial dependency. What happens to spatial dependency?
So that was the so we're able to eliminate them in favor of this sink term, and that sink term basically says how you scatter from the homogeneous modes into the heat carrying modes that take the heat out of the system to the boundary.
GK is a distribution function of what?
Sorry?
What is GK, the distribution function of?
GK isn't a distribution function, so this one here described is a source term for Landau-Zener tunneling. So it describes the production of pairs from the vacuum. And this, again, is, well, it basically describes the disappearance of carriers into those modes that carry heat to the boundary of the sample.
Andrew, you're officially out of time.
Okay, so I can wind up now. Yes, so one final point here. You find that when this is very highly boosted, that actually the phase space for scattering is restricted, so you're dominated by outscattering. And that leads to approximations that are very similar to those that we were able to use in this 1/n trick. So it might be that actually some of these features of the pro-brain calculation or of the 1/n calculation are actually dynamically self-consistent in these out-of-equilibrium systems. So here's my conclusion slide. I reckon I have 1 minute 30 seconds left. But,
I believe you.
so there we go. Quantum critical systems can be universal out of equilibrium. That's the main point here. And steady state can be far from equilibrium. And in the field theory, we can get equilibrium results and far from equilibrium results. And holography seems to allow us to interpolate between these in a very attractive way. It even suggests there may be a general principle that these fluctuations can be thermal even though we're far from equilibrium. A word of warning, the role of the heat bath is delicate. The questions of thermalization, large N, and so on. And I think this idea that we may possibly be able to see universal steady states in a system that is nevertheless evolving in some of its other degrees of freedom is quite an attractive one. And we'll actually get round some of these delicate issues of the heat bath. If the system connected as its own heat bath, then we don't need to worry as much. Okay, thank you.
Despite my concerns, there's time for one short question. Perhaps Hong. Yeah.
Okay, it seems like both from your calculation, the epsilon calculation, and also maybe from ADS point of view, seems like once you go away from this probe approximation, then this effective thermal thing won't happen. Is that right?
Well, I think it does in the epsilon calculation. You still see it there.
What you said, if you do a self-consistent effective, then you don't actually.
No, I should. Maybe that is what I said, but I didn't talk about noise here in the epsilon expansion.
Oh, right.
You still get this effective thermal distribution.
Still have that behavior.
Yes. So also there's a question about whether back reaction really describes the physics that you want to describe in an out of equilibrium steady state. If you really have a situation where you have some external heat bath into which you're dumping the energy, it may be possible to form an equilibrium steady state distribution, which will not be described. You will not require back reaction to describe that. So it may be that this can still be achieved. This question of whether there really is a thermal distribution of the fluctuations or not, I don't know. On the condensed matter side, there have been a couple of calculations that have shown it. In a way, they're a little ad hoc. We're still learning how to treat these out of equilibrium systems. And so, if we can ask the question in a more controlled way in another context, perhaps we can get insight into it.
Sounds like wise words to end this session. Let's thank Andrew again.